Dear students, today I am going to discuss module 3 digital signal processing. In that module we are going to discuss about all poles analog filter, Butterworth and Bhebyshev. Okay, here we are going to discuss about the pole design of your Butterworth filter and the Bhebyshev filter, and then frequency transformation. So now here in our syllabus it is given Bhebyshev filter type 1. So here the magnitude response is equiripple in the pass band and monotonically in the stop band, decreasing in the stop band. The Chebyshev type 1 filters are all pole designs. Okay, here it is all pole filters. Here all the poles will be present. Okay, so here the IAR filter I told it is regressive filter. Okay, IAR filters is the regressive filters. So all the poles will be present. That is nothing but in the transfer function the denominator equation will be there. And here the normalized magnitude function will be given by 1 divided by square root of 1 plus epsilon square at the cutoff frequency omega c. Okay, and here the magnitude response approaches the ideal response as the value of n increases. N is nothing but your order of the filter. And the next one is Butterworth filter. The Butterworth filter is also all pole designs because this both Butterworth filter and the Chebyshev filter both we are going to discuss for IAR filter. So here we are going to design the all pole analog filters, and here the filter order n completely specifies the filter. Okay, and the magnitude response approaches the ideal response as the value of n increases. Both in Chebyshev as well as the Butterworth filter, the value of the n increases means your the response curve will be flat. It will be ideally flat from the origin. Okay, where it starts decreasing, and the magnitude is monotonically decreasing as the function of omega. And at the cutoff frequency, the magnitude of the normalized Butterworth filter is 1 divided by square root of 2. Hence, the dB magnitude of the cutoff frequency will be 3 dB less than the maximum value. Okay, in the Butterworth filter, there is no ripple in the pass band, but in the Chebyshev filter, there will be ripple in the pass band. In the stop band, there will not be ripple in the Chebyshev filter. And now we will discuss about the frequency transformation. So actually, if they ask in the question for the given transfer function, that is for the given filter response, suppose if they give low pass filter prototype into another configuration like high pass, band pass means in the analog domain, if you want to do the transformation, we are going to use this type of frequency transformations. Okay, suppose if you want to transfer low pass to low pass means the S will be replaced by omega p divided by omega p dash into S. Okay, and the band edge frequencies will be omega p dash. And if the low pass to high pass means S will be transferred to omega p into omega p dash divided by S into omega p dash, sorry, omega p dash. Actually, this frequency transformation will be useful only for your analog domain. Okay, so that is nothing but analog domain is nothing but S domain. In S domain, if you want to do frequency transformation, we can do this type of transformation, that is low pass to low pass means the same low pass filters, if the given specification is low pass, then if you want to transfer same low pass means the S will be replaced by omega p divided by omega p dash into S, and the band edge frequencies will be omega p dash, and the high pass will be S tends to omega p into omega p dash divided by S, and the band edge frequency will be omega p dash. And the band pass means the band of signal will be passing, so you will have upper frequency and lower frequency band frequencies. Okay, so the S domain, that is analog domain, the S will be replaced by omega p into S square plus omega L into omega u, and divided by S into omega u minus omega L. Omega L comma omega u. This is lower cutoff frequency, higher cutoff frequency. And for band stop, S will be replaced by omega p into S into omega u minus omega c divided by S square plus omega u omega L into omega L into omega U. This is the frequency transformation in the analog domain. Suppose if you want to do the frequency transformation in digital domain, then same thing if you want to do, but same low pass to low pass means in the digital domain you are going to use omega to the power minus 1 tends to omega z power minus 1 tends to z power minus 1, that is z inverse minus a divided by 1 minus a into z inverse. Omega p is the band edge frequency and a is the sine of omega p minus omega p dash divided by 2 divided by sine omega p plus omega p dash divided by 2, and omega p dash is the for the high pass filter. We know that high pass filter, and this is omega p is nothing but your band edge frequencies. And if you want to transfer from low pass to high pass or high pass to high pass in digital domain, this the z inverse will be replaced by z inverse plus a divided by 1 plus a into z inverse, and the data will be given omega L. This is for band pass. This z inverse will be replaced by z power minus 2 minus a1 into z power minus 1 plus a2 divided by a2 z power minus 2 minus a1 z power minus 1 plus 1. And omega L is the lower edge frequencies, omega U is the upper edge frequencies, and then a1 is minus 2ak divided by k plus 1, a2 is k minus 1 k plus 1, and alpha is the cos omega u plus omega L divided by 2, and cos omega u minus omega L divided by 2, k will be the cot of omega u minus omega L divided by 2 into tan of omega p divided by 2. And for band stop, this z inverse will be replaced by z power minus 2 minus a1 z power minus 1 plus a2 divided by a2 z power minus 2 minus a1 z power minus 1 plus 1. So omega L, omega U, a1, a2, all the what is the corresponding coefficients and what is the name of the coefficient. Actually, in the given problem, if they ask transfer low pass filter to low pass filter to high pass filter. If they ask in digital domain or analog domain, we can use this transformation technique. So this is about your frequency transformation technique in digital domain. Okay, so in the problem, this transformation technique can be used both in Butterworth filter as well as the Bhebyshev filter, and here both Butterworth filter and Bhebyshev filter are the all pole design filter. Okay, so we are going to all pole design filter is nothing but the transfer function consists of the denominator coefficients. Okay, so it consists of both numerator and denominator. All pole filter means you are going to design using the denominator poles. So only it is called as a all pole design filter of both Butterworth as well as the Bhebyshev filters. In actually in the next coming classes, we will discuss about the problems using frequency transformation also we will be used, and also we are going to discuss about the all pole design filters. Okay, how we are going to design the analog transfer function, and using transformation technique how we are going to convert into digital filter. Everything we will discuss while doing the problem. Thank you, students.